So now we're on lesson 3.2 for physical science, and it's all about Newton's laws. Law 1, 2, and 3. And I feel like this gentleman that you're about to watch is going to do much better job than I could. And I like how he's incorporating talking with motion that you can actually see, because this is a very physical, hands-on unit, as you will see in class with all the projects that we will be doing. So today, just follow along with what he's doing. If he has it written down, you should write it down as well.
Law of inertia. It's also called Newton's first law of motion. Simply stated, it means an object in motion tends to stay in motion, or an object at rest tends to stay at rest unless the object is acted upon by an unbalanced force. What's an unbalanced force? Well, I've got a tennis ball right here, and I can apply a force to it, but it's not moving, right? It's still staying steady. That's because this isn't an unbalanced force, this is a balanced force. The force down on the tennis ball is equaled by the force on my hand pushing up on that ball. If I push the ball in this direction, it's going to move. So that's what we're talking about. Okay, this is a pretty common sense example, and you can state this pretty simply as stuff wants to do what stuff was doing. And any good waiter or waitress knows this practice. When they fill your coffee cup, if they know Newton's first law, they don't fill it all the way up, right? Because if I've got your coffee cup and I start to go to the table, well, that coffee wanted to stay at rest. It's going to stay at rest and it's going to spill off the back end, right? When I get to your table, I'm in a constant motion, and I stop and put it on your table, that coffee wants to keep moving, and it's going to splash out of the cup onto your table. So, any good waiter or waitress that doesn't spill coffee when they're giving it to you understands Newton's first law of motion, the law of force and acceleration. This is also known as Newton's second law of motion. There's three components to Newton's second law. The first one is that a force on an object will cause that object to accelerate. The second is this acceleration is directly proportional to the force. So the harder I push, the harder it accelerates. Okay? The third is this acceleration is inversely proportional to the mass of the object. So if I'm pushing an empty shopping cart, I'm going to be able to get it to go a lot faster than if I'm pushing a shopping cart that's full of groceries. Okay? So, makes sense. And we can show this relationship by Newton's formula over here. Force equals mass times acceleration. Okay? So let's do a practice problem that you might see, which is a good application of Newton's second law of motion. Okay? Let's say we have a rocket in space, so there's no air resistance or anything. It's accelerating at 40 meters per second. But while it's accelerating, it's losing mass because it's burning fuel. The fuel is actually becoming the thrust that's causing it to accelerate. So at a point where it burns up half its mass due to fuel loss, and the thrust is tripled, what is the acceleration going to be at that point? Okay? Well, if we say that force is mass times acceleration, and we say that the thrust is tripled during this time, but the mass is decreased by 1/2, then what happens to the acceleration? Okay? So we're going to say x is the change in acceleration. Okay? Well, if I say this increases by 3, and this decreases by 1/2, then our acceleration must increase by 6 times. So 6 times 40 meters per second is 240 meters per second squared, which is the acceleration at that point in time. And that's one of the reasons rockets do accelerate in space, because they're losing mass. That loss of mass conversely increases their acceleration. Okay? So this is a good practice problem that kind of demonstrates Newton's second law of motion. Let's talk about force. Force is anything that causes an object to accelerate or decelerate. Okay? Newton discovered this principle of force, and he came up with his formula, which is very widely used, and you're going to have to use this a lot to solve physics problems. Okay? The formula is force equals mass times acceleration. Okay, so what are the units for force? Well, we know the unit for mass is kilogram. The unit for acceleration is meters per second squared. So the unit for force is really a unit of mass, kilograms, times meters per second squared. Okay? Now that's a lot to write, and I don't want to have to keep writing that every time I'm writing a force. So we can simplify that. We can say 1 kilogram times meters over second squared equals 1 Newton. So when we write a big N, named after Sir Isaac Newton, the man who discovered this. We're talking about 1 kilogram times meters per second squared, the mass times the acceleration. Okay, there's a couple different formulas you're going to need to use to solve problems. And typically they'll ask you, using this equation, to, given two of these things, solve for the third. So given a force and a mass, solve for acceleration. Given mass and acceleration, solve for force, and so forth. So we can very easily move these around. So we know that F equals m times a, okay? But if we want to solve for acceleration, we can say, okay, well, I want to get my m. I want to divide by m here, divide by m here, and I have acceleration equals force divided by mass, okay? If I want to solve for mass, I can again remove my a from this side by dividing, and I get mass equals force divided by acceleration, okay? So let's look at some of the problems that you'd get typically with understanding Newton's laws of force, okay? The first question might be, what force is required to accelerate an object having a mass of 3 kilograms to an acceleration of 5 meters per second squared? Okay, so they've given us mass and they've given us acceleration. So that's just a simple F equals m times a. And if I say 3 kilograms times 5 meters per second squared, okay, I get 15 meters, don't forget my kilograms, times meters per second squared. And again, I don't like that unit, so I'm just going to call that 15 newtons. Okay? Pretty straightforward. Let's look at a second problem. This time I'm going to ask something a little bit different. Okay? What is the mass of an object accelerated at 10 meters per second squared to a force of 75 newtons? Okay? So now I want to know the mass. Okay? So again, and this time I'm saying m equals F divided by a. Okay? And if I plug my numbers in here, okay, I've got my force is 75 newtons, which cancel the units. We'll say is kilograms times meters per second squared. Okay? And my acceleration is 10 meters per second squared. Okay? And now you can see that this unit cancels with that unit. Okay? And I have 75 divided by 10 kilograms, which equals 7.5 kilograms. Okay? So these are some of the ways we can apply this unit of force, F equals ma, to solve different types of problems. Let's talk about net force. This is also sometimes called resultant force. Those two words are used interchangeably. And basically what this is a vector that's produced when two or more forces act together. Remember, anything that has distance and magnitude we can depict as a vector. So let's look at a couple of examples of how we can calculate a net force on an object. Okay? Let's take, for example, a helicopter. You may notice when helicopters go up and down, they are completely vertical, right? But when they want to go forward, they need to actually tilt. That's to create this thrust where they're pushing air in that direction, which is causing a force in that direction. I'm going to call that F1. Okay? Well, how come that helicopter that's tilted in this direction isn't going up in that direction? Well, that's because there's a second force acting on that helicopter. Okay? That's the force of gravity. I'm going to call that F2. Okay? So, what's the overall force going to be on this helicopter? Well, I have to add my two vectors together. And I can do that easily by just taking this one and putting it head to tail to the first one. So, if I put my F2 right here, I can see that my resultant vector, which we'll call FA, is causing it to move in a horizontal way to the Earth. Okay? So, just adding vectors, that helps us figure out the true vector. Okay? Let's say I'm playing golf. Another example we might see, I'm going to tee off from right here, and there's my hole, and I want to aim right for that hole. Okay? And I'm going to hit a shot that goes right about there. Okay? Now, if that was my only force acting on that, well, that'd be a pretty good shot, right? But let's say there's a wind, and let's say that wind is blowing in this direction. Okay? So F1 is the force applied from my golf club on the ball. F2 is the wind. Okay? That is going to push the ball in this direction. Okay? So So if I put F2 right there, and I add these two vectors together, I actually get something that looks like that, F actual, okay? And now I'm off in the rough, right? That's not a good shot because I didn't factor in what the wind was going to do to my ball. The force of the wind on my ball has actually made the actual vector far off of center. So these are some of the ways we can add vectors and see how forces interact together to create actual true vectors. Let's talk about the law of action and reaction. This is also known as Newton's third law. And this simply states that for every action, there's an equal and opposite reaction. So if I apply a force onto an object, there's a reaction force that's applied back on the force that's being applied to it, okay? And we can say that if the force is going to equal, we'll just say F1 is going to equal negative F2. So those forces apply in opposite directions and they cancel each other out. So you don't usually have to solve problems with this, but you'll oftentimes be asked in a question, say, for example, if a big bat is hitting a ball at 1,000 newtons, what is the force of the ball on the bat? And you might be confused because the bat's big and the ball's small, but remember, for every action there's an equal and opposite reaction, which means simply that the ball is putting the same force of 1,000 newtons on the bat. So really, regardless of size, they are equal and opposite forces applied to each other. So that's a question you might see on a physics problem, and you can answer it, again, using Newton's third law of motion. Let's look at some force, body force diagrams. These are basically diagrams that show the force or forces that are acting on an object, and they help us illustrate how those forces interact to move that object or not move that object. Let's look at a couple examples. Let's take a book, okay, and if I have my book and I drop it, there's obviously a force that's acting on it, right? That's the force of gravity. But if I have my book and I hold it on a table, okay, gravity is still a force applied to that book, but the book is not moving, right? There's no change in the book. So there's another force that's acting on the book, and that force is what we call a normal force. So if I do a diagram of my book, I've got a force down, which I'm going to call Fg, force of gravity, okay? But I have another force acting up on that book, and that's the normal force. That's the table applying an equal force on that book so that book doesn't fall to the ground, okay? Let's look at a falling balloon. Now, the reason we're using a balloon is I want to have something that is falling at a constant velocity, okay? Because if it's just falling like that book, we pretty much have just the force of gravity, right? Okay, but that falling balloon with a constant velocity, again, has the force of gravity, Fg, forcing it down, okay? But constant velocity means it is not accelerating, it's moving at a constant velocity, so there's another force acting on it here, and that is the force of the air friction, or air resistance, which is pushing up on it, okay? So two forces on that falling balloon, okay? Let's look at another one. Let's take the book on the table, and now let's move that book along the table, okay? So I obviously have a force of acceleration, which I'm applying to the book to cause it to move, okay? But as I'm moving it across the table, there's another force pushing against, and that force is the friction of the table, okay? So it's applying a force back on that book, okay? I also have a force applying downward pressure on there. That's the force of gravity, okay? And then I have a force, equal force going up, which is the normal force, the force of the table being applied back up to the book. So see, these are some of the ways we can use a diagram to illustrate all the different forces that interact on moving and stationary objects.
That concludes this lesson over all of Newton's laws, as well as a few things having to do with force. That's going to lead us into our next section, which will be lesson 3.3.